In this video, I'll go over another common approach for numerical integration of functions called Gauss quadrature. And that term quadrature, incidentally, just means numerical integration. After studying this video, you should be able to understand the conceptual basis for Gauss quadrature and also understand how Gauss quadrature constants can be determined, and use Gauss quadrature to calculate the integral of a function. So here's the basic idea of Gauss quadrature. So here's a function, and for a trapezoid method, recall, we use something like, we use the endpoints of the integration range a to b to evaluate the integral of the function, and we got an error that was proportional to the curvature of the function as well as the cube of the range of the integral. Well, the basic idea of Gauss quadrature is to evaluate the area by joining any 2 points on a curve rather than simply choosing the endpoints, and then to strategically choose the line that we use so that the positive and negative errors are balanced. So this second graphic here kind of indicates what I'm talking about. So if we're integrating over a range from a to b, that's still the trapezoid that we're going to use to calculate the integral, and this would be for a 2-point calculation. We can use more points as well, but for a 2-point calculation, but we've strategically chosen these points so that the positive error here is balanced by the negative error here and here. And we can do this for a 2-point formula, thinking about this as a line, or a 3-point, and higher is conceptually the same. It's conceptually the same idea. So let's look at how we would do that. And the first thing we'll look at is the Gauss-Legendre formulas, which are a type of Gauss quadrature where we take integral estimates of the form I equals some c naught f of x naught plus c1 f of x1, basically a linear combination of function evaluations. So again, we are strategically finding the x points that we're going to take those function evaluations at, and then also the c sub i's, and those c sub i's we call the weighting coefficients. So we can write this concisely as our integral is equal to some summation of the c sub i's times f of x sub i's. And the next thing we need to look at is how do we figure out what the c sub i's and the x sub i's. And there's lots of different approaches to do this, and I'm going to just cover the Gauss-Legendre approach just to give you a conceptual idea of how this is done. So let's look at a 2-point Gauss-Legendre formula. So we would have 2 unknown weighting coefficients and 2 unknown x values to evaluate the function at. So in total we need 4 equations to determine our 4 unknowns, c0, c1, x0, and x1. And the approach for Gauss-Legendre is we're going to assume that the integrals of the functions y equals a constant, y equals x squared, and y equals x cubed are computed exactly by our formula. And we'll use those 4 constraints to develop 4 equations. We're also going to simplify the math by assuming the integration happens over an interval of -1 to 1. this means that when we apply this, we'll need to shift whatever our actual integration range, AB, we'll always need to shift that to the range -1 to 1. We'll talk about how to do that in a minute. But first, let's look at how we solve for these constants. And what we'll do is just use each of these constraints to set up 4 equations. So to determine the constants, we'll start by taking the integration of a constant, and that constant will just use 1 from -1 to 1, and we'll set that equal to our Gauss-Legendre formula. The integral of x from -1 to 1, set that equal to our Gauss-Legendre formula. Integral of from -1 to 1 of x squared dx, and integral from -1 to 1 of x cubed dx. So evaluating those integrals, we have the integral from -1 to 1 of 1 dx is just x evaluated from -1 to 1, or 1 minus -1, or 2. The integral from -1 to 1 of x dx is going to be x squared over 2 evaluated from -1 to 1, which is going to be 1/2 minus -1 squared over 2, and that squares away the negative sign. That goes to 0. The integral of x squared dx is going to be x cubed over 3 evaluated from -1 to 1, which would be 1/3 minus -1 cubed over 3, which is equal to 2/3. And the last constraint gives us x to the 4th over 4 evaluated from -1 to 1, and that's going to be 1/4 minus -1 to the 4th over 4, and again that's equal to 0. So here we have 1, 2, 3, 4 now algebraic equations for our 4 unknowns, C0, X0, C1, and X1. And we can go ahead and solve those 4 equations for the 4 unknowns, and the results are shown in this next table here. So here's the constants. So for the 2-point Gauss-Legendre formula, the constants C0 and C1 each come out to 1.0, and we take our function evaluations at -1 over root 3 and x1 at +1 over root 3. We could then take a similar approach to develop a 3-point Gauss-Legendre formula, and in this case we would add constraints, integral from -1 to 1 of x to the 4th, and making sure it's also exact for integral from -1 to 1 of x to the 5th. So we could add 2 more constraints to solve for those 2 more constants, and that would give us a 3-point Gauss-Legendre formula, and we could do the same thing for a 4-point Gauss-Legendre formula. Now we don't need to go redo those integrals every time. Once we've determined these constants, we can just use them. So we'll see an example of how to do that in a minute, but first let's get back to that problem of shifting the integration range to be from -1 to 1. So we want to apply this to solving any integral that's for an integration limits from a to b, but we derived this using integration limits of -1 and 1. So in order to implement this integration approach, we're going to need to introduce a shifted integration variable, and we'll just call that variable xd, and we're going to just assume that xd is linearly related to x. And in doing so, we would have x is equal to a1 plus a2 xd, and we just need to find a1 and a2 in order to carry out this shift. And we can do that by setting these 2 equations. We know that when xd is equal to 1, so a1 plus a2 times 1, we want x to be equal to b. So that's going to be our upper limit of integration. Similarly, a1 plus a2 times -1, when xd equals -1, that should mean our original variable x should be equal to a. And so we can just use these two equations to solve for, this is now just a linear system for a1 and a2, so we'll solve for a1 and a2 for any specific problem. So let's do an example. So here we're going to use a 3-point Gauss-Legendre quadrature formula to estimate the integral of 2x plus 3 over x quantity squared, all evaluated from 1 to 2. So this would be an integral that would be kind of a pain to calculate by hand. We could calculate it using something like Wolfram alpha, but we'll use this here to practice how to implement a 3-point Gauss-Legendre quadrature. So from the table, that 3-point Gauss-Legendre is going to be I is equal to 5/9 times f evaluated at negative square root of 3/5 plus 8/9 times f evaluated at 0.0 plus 5/9 times f evaluated at the square root of 3 over 5. So again, those results are just coming from this table here. There's the 5/9, 8/9, 5/9, and here's the x locations where we're taking those function evaluations. So that's our formula, but before we can't just plug in the 3/5 in here because the limits are from 1 to 2. And remember, this is going to be our shifted xd variable that we plug in. So we need to figure out this new equation in terms of xd. So to do that, let's set up that linear system. So we're going to have 2 is our b is equal to a1 plus a2 times 1, and 1 is equal to a1 plus a2 times -1. And we can solve that linear system, and you'll solve for a1 is equal to 1.5 and a2 is equal to 0.5. And then we will also, so now we know that x is equal to 1.5 plus 0.5 xd. Now, similar to when you do a u substitution in calculus, we also need to calculate what we're going to substitute for dx. And so we see dx is equal to 0.5 dxd. So we'll plug those back in as our integrand. So our new integral here is I is equal to the integral from -1 to 1 now of, and now we need to plug all this in. So we have 2, and then substituting in for x, 1.5 plus 0.5 xd plus 3 divided by 1.5 plus 0.5 xd. This whole thing is squared, and then substituting in for dx, we have 0.5 dxd. Now we're ready to plug things into our function and evaluate our Gauss-Legendre formula. To do that, we need to recognize what is our f, and our f is everything inside our new integrand. So that's going to be our f of xd, and we'll just plug in those function evaluations as shown up here. And when you plug that in, you will get a result I of 25.8345. And you can compare that to the exact true integral calculated analytically is 25.8333. So we can see that this is a very accurate estimate of that integral. And it was calculated fairly easily with 3 function evaluations after doing that variable shift. So the key to implementing Guass Quadrature is understanding how to shift the variable as necessary to get our integration limits in that -1 to 1 range. And just to be clear, this approach I've talked about in this video is the Gauss-Legendre approach to quadrature, but Gauss Quadrature in general refers to that basic idea of taking and strategically using a linear combination of function evaluations to approximate an integral. And you can use other strategies besides the one that we used, developing the 4 constraints based off of these 4 exact integrals. You can use other approaches to developing those constants. And we're not going to go into that in this class. I just wanted to illustrate conceptually how we do this. But you should be aware that there are alternative strategies for developing these constants, and make sure you're paying attention whenever you're using a Gauss Quadrature formula. And that concludes this video.